Just a reminder, this is being recorded. It'll be up on my YouTube channel probably by about noon Pacific time. This will be daily until we finish. And given I've had some recording problems here and there that, this might take a little longer. We'd gone through and just discussed the concept. I know this is a little more dramatic and doesn't have my disclaimers. You have to go to part one or the first half of part 3 to get all the disclaimers. Sorry. We talked about this problem of reverse fast forwarding and these PIM joins from receiver out to sender. And what we were talking about was the shortest path or source distribution trees. So you'll see those, that language used, and in your IPM route, you'll see this S, G, where S is a unicast address of a sender, and the G is a multicast group IP. So that's the class D, and that'll be class ABC for IPv4. And the traffic, the actual traffic, this guy's sending, he sends it, shortest unicast path based on routing protocols, on the unicast routing protocols. So RIP, this is going to be straightforward. It's going to count hops, right? If this was OSPF or EIGRP, that we would be looking at the costs, the bandwidth delay across the path to get our best path. But that's how we're going to do it. That's how we're going to establish this shortest path or source distribution tree. And each source distribution tree is independent of one another so that they each do their own calculations. So from this sender, the shortest path goes to the right, to the other sender, it goes to the left, based on that one router down the bottom right. So that's as simple as this gets. And as I've mentioned before, there was a specific multicast routing protocol, but given the timing of it and how memory was so dear, CPU cycles were so dear that rather than set up this whole separate routing protocol that has its own overhead, we're going to do unicast, which does create some problems. For example, if this link here is actually going across a WAN circuit, and it's a layer 3 circuit, MPLS, layer 3, and your provider isn't supporting multicast. There are ways around that, but it's a little more complicated. So, and then we have a shared tree. So the shared tree introduces this concept of rendezvous point. So you think about that word rendezvous, you go back to the old, the very early West in the United States, rendezvous where trappers and merchants would meet to exchange beaver pelts for money and goods that they needed. So this is a place we have to know, we all have to know where that RP is, and we're going to explain that later. In the shared tree, when I get it, I'm a last hop router. So the ones closest to the senders are first hop. The last hop router is closest to receiver. The last hop router, when I get that IGMP report, we talked about IGMP last week, that I want to build a tree back to the rendezvous point. Because at this moment, I don't know about the sender. The rendezvous point is going to help me do that. Now, remember with IGMP version 3, you can know about the sender, so you can bypass this rendezvous point. You don't have to have a rendezvous point. In fact, you don't have a rendezvous point for IGMP v3, source-specific multicast. But for the other forms, there's a rendezvous point. So they're going to build this tree back, and this is the shared distribution tree. And you're going to see a star instead of a unicast IP address. And with the shortest path distribution tree, the incoming interface, the one that will accept multicast, always points back. It's the unicast interface that's the most direct path, the best path back to the source. So you'll see this would be an incoming interface, this would be an incoming interface, this one, and an outgoing is in your IPM route table, you're only taking in one copy, and then you're distributing it to all the links that need it. So this router, for example, has an incoming interface here, and he has an outgoing interfaces on these two interfaces. So if this is E0, and this can be E1, E2, that incoming E0, outgoing E1, E2, okay? And in this one, incoming is always back towards the rendezvous point, and then outgoing is all the interfaces. So if this was a multi-layer switch and you had a lot of SVIs, a lot of interfaces, and you had multicast turned on a lot of them, most of them, all of them, and they all wanted this traffic. And one of the common, if you look up SSDP, it's pretty common for the zero config. It's for home networks really, but your enterprise machines still do it, that you'll see lots of outgoing interfaces because there are lots of that are running that protocol, and so they're doing that IGMP report, and then they're pointed back towards a rendezvous point. If you see the rendezvous point, if you see that outgoing interface is null, the device thinks it's a rendezvous point. Doesn't mean it is in your design, it means it thinks it is. And when we get into rendezvous points, you'll discover more about that. So this is just the basics of, you have a source tree, you have a shared tree. Now, with any source multicast, which is the most common that we run into, is a sender ends up creating, if I just start sending, no receivers, that this first hop router, assuming we built our network right, knows about a rendezvous point, and it will actually send the traffic to it'll send its traffic to the rendezvous point, and the routers along that path are going to get both a shared tree and a source tree pointed to this rendezvous point. And we're going to go into a lot more detail on that in upcoming lessons, but that's just the basics. So you'll normally see both in any source multicast, both this star comma G and the S comma G, even if there's just a sender. Now, if there's only receivers, you'll only see the star comma G. You only see the shared distribution tree, because there are no sources for the rendezvous point to connect to these senders. So there won't be any unicast address of a source sender. There only is a star comma G, which basically this rendezvous point and these routers on the path to the rendezvous point, they know there are parties that are interested in receiving traffic when and if it ever exists. Okay. Source or shortest path trees, more memory, because you got to track all the sources. So with any source multicast, that's one of its downsides. They will, regardless of where the rendezvous point is within the network, assuming PIM is turned on and you're not blocking, that they will go to the optimal path. They will go to that shortest path. Now, there are times that doesn't make sense, and certainly your placement of RPs with a bidirectional where the rendezvous point is integral to the path, and we'll go over bidirectional very briefly in a future lesson, that the placing of rendezvous points is very important. With any source, they're still important. They need to make sense. They need to be accessible, but they're less of an issue than with something like bidirectional. Shared trees, well, since I'm not tracking every single source, that it in typical is going to require less memory. When you look at something like SSDP, and you're going to see that if you show IPM route and you look at 239, 255, 255, and I believe it's 252, but you'll see on a large enterprise network, you may see if you have very generic rendezvous points, or even on a big layer 3 switch, you'll see plenty of senders and lots of outgoing interfaces. We track all that stuff, takes more memory, right? The shared tree, just notice about suboptimal paths and introducing delay. Sure, I put the rendezvous point kind of in a corner somewhere, and I've got a lot of hops to get to it. It goes across some, say, highly utilized or very low bandwidth WAN circuits. That sure, I can absolutely do that. they're not going to stay with a rendezvous point. They're going to use a rendezvous point to connect, unless you're bidirectional multicast. Now, I've never done bidirectional in a corporate network, so I can only speak to from lab experience, but just want to bring up those points. And if you went through my classes before, you remember that I shunned bidirectional. It has its place. Everything does. A PIM join is used to create a tree, and a PIM prune is used to remove the tree. Now, it sort of removes it. In a lot of cases, you're going to see, and there'll be on your show IPM route, there's a P flag for pruned. You can look through the definitions on top when you run the command, and sometimes those will stick around for a while because they still have a purpose. They may need to get reactivated, but it's saying I'm not actively using this one. The shortest path trees, the PIM control messages, the join and prune are sent towards the source. So if I am, say, this router, and if for some reason I had joined this and now I no longer have a sender, so I'm no longer needed to communicate with this rendezvous point, this router sends, this is well, if the source tree, for example, if this was doing it, and he's talking about this source, he doesn't want this source, he's going to send a prune to this router. He's going to tell this router, don't bother copying that traffic and sending it to me. I don't need it anymore. So in a join, he would send a join out this interface to this router to say, I understand you're on basically you're on the path to this source. I need that traffic. Please give it to me. He doesn't know, there's no intercommunication between them that's saying, hey, I know you have that traffic already. It just says, hey, my best unicast path to that sender is through you. Give me. Not a very polite protocol, I guess. And then the shared trees and the messages are sent towards the RP. That's who I'm trying to join towards. Now, we have some variants. We have dense mode. You don't need an RP in dense mode. Essentially what I do is when a sender comes online, he starts sending joins out, the first hop router sending joins out to all its interfaces. And then everyone else participating in dense mode does the same thing until we reach the edge of the network. And then as I have no more PIM neighbors, I can send back going, I don't have anyone who wants this traffic, and prune back. And it's no longer supported on your traffic. It's crude, but when you first build this, a lot of these things like doing rendezvous points seem kind of complicated. I can just do this. This is how it'll work. And you'll see Cisco has Sparse-Dense mode. And what that is to say, I'll use this next one we're going to talk about in a second. If I have a rendezvous point, if I don't, I'm going to go to dense mode. And even if you're running sparse mode in Cisco, if you use auto RPs, you're still actually running some dense mode. The communication about the auto RPs is done in dense mode because I can't learn about where a rendezvous point is if I need the rendezvous point to be able to learn it. That's circular, right? So in dense mode, no RP, everything is shortest path tree, and is no longer supported. Sparse mode, and you're going to see sparse mode only on the newer platforms like Nexus, that it needs it needs an RP. It does a shortest path tree. It does a shared tree as well. So the senders are doing a shared tree back to the RP. The receivers, the senders are doing a shortest. They're going to connect to the RP. They're going to send that traffic out to the RP, so the RP knows about it, so it can tell the receivers about it. So it's doing both shared trees, source trees, and then once the receiver learns, that last hop router learns about the source, it can switch to a source tree and optimal route. Source specific multicast, okay, it only does shortest path tree because you're telling it about the sender. There are some ways the application can tell you about it, and it may have an out-of-band mechanism. It could be programmed with it. It could be, it has some sort of like web lookup. There are other mechanisms the router can use, like DNS, or in some cases, you can design, I've seen a design like this where you're doing InformaCast with Cisco phones. You're only doing source specific with the phones. So just send all the source specific traffic to the cluster, whatever the InformaCast server is, send it there and it'll sort it out. It's a way to do it. And then at least along the path, they know how to get to the source, the InformaCast server. It's not very flexible, but it's a way to do it. And then bidirectional, there's no shortest path tree. Everything has to go through the shared trees. The reason is that it's unlike normal, the rest of multicast, I don't allow traffic in the same interface I'm sending out of. Now this is per group. The idea with bidirectional is that I may have more of like a, say a messaging app that we're all communicating together, and that I may need the traffic to loop back out that interface. So bidirectional allows two-way traffic. The concern is looping with that one in particular. So my old instructor from years back was just avoid it if all possible. And I still see that advice in other sources. I haven't checked with the latest gurus to see if that advice has changed at all, but generally it's avoid bidirectional. So here's all our components. We've talked about PIM, protocol independent multicast. So that's how layer 3 goes between, the multicast goes between layer 3 interfaces. We've seen IGMP, that's on the layer 2 side. That's the LAN side. That's how we get from the receiver. The sources don't participate in IGMP. They just send. So from a source, it's going to be I send. I do PIM from the first hop router out towards a rendezvous point, and then eventually I do PIM to a last hop router, and IGMP is between the last hop router and the receiver. Okay, we haven't talked about MSTP yet, multicast source discovery protocol. We've just mentioned rendezvous points. We haven't really talked about boundaries yet. We're going to get to all this good stuff. So a little shorter today. I know I could have run long on Friday, but I'm trying to keep these more digestible chunks. Also, this gives us some time to ask questions. Chat window's open if you have questions. That find chat in your Zoom client. So you now know a little bit more. And I'm going to say, so on what interfaces will I need to enable PIM? So you got to think about all the pathing of how I'm going to make this work. And remember from Friday, we had things like the equal cost. Oops, I didn't want to do that. Equal cost scenarios, right? That we want PIM enabled. Like in this scenario, we'd want PIM enabled on all these interfaces. If for nothing else, for the redundancy in case this fails, but you need to deal with this, and that's your multipath command. Or I'm going to cheat and I'm going to do my unicast, and I'm going to put some sort of delay or other add cost to it somehow or another, add hops if I need to, like a route map, to make this less desirable. So I force all the traffic through that set of links, but I may not want to do that. I may like having my redundancy. And so that think about where you need to enable PIM. And the PIM mode. So just take dense mode off your plate and take Sparse-Dense off your plate. Sparse-Dense is just not supported on the newest platforms. That is at this point, I would not do a design Sparse-Dense. There are vendors for a long time like Vocera that encourage you to use Sparse-Dense because they didn't trust you to do your multicast network right. And they were right, to be honest. And so with Sparse-Dense, there was a fallback, like no matter how badly you do this, particularly if it's in a campus LAN, it's just it'll figure itself out, it'll be fine. But you can't do that anymore. So taking a look at your applications, what do they want? Or is there a specific, My advice on this one, bidirectional only if you absolutely have to. Avoid dense, sparse dense, like they're the coronavirus. Wash your hands, stay inside. Don't do it. Don't touch it. Sparse mode, source specific are the two most common. If an application supports sparse source specific, it's a great thing to do. Just you need to figure out the engineering on how you want to do, how you want to build the source specific. Is the application going to handle the finding sources, or do I need to do more at the network layer? And then this question about application boundaries, you saw in the chart, I did have something about boundaries. Those are more like ACLs. This is just continuing to explore that. Where's the edge of the application? So if I have senders at one site, the server in a data center at a different site, receivers spread out through all kinds of sites, well, the WAN's going to be involved for that application. If it's contained inside a single VLAN, I may be able to go really simple. If it's in campus, and so there's servers on a server LAN and there are receivers on a receiver LAN, and I've got wireless controllers and APs, and they're all taking up different VLANs. Okay, you want to map this out so you understand what, if you haven't picked groups yet, this will start to tell you, I should probably create this enterprise-wide block. I need to have this campus block. I have this just LAN block. What do I want to do with that? That can help you sort of figure that out. But if you need to know what the boundaries of the application are, and you need to be in, of course, in partnership with your touch and face bad. You need to be in consultation with your application folks, because they need to tell you, we're going to expand Vocera. We're going to use the same Vocera instance across these ancillary small sites that are across the WAN. So you can design something and say, we're not doing that. And your application folks come back and go, well, actually you are. And rather than having to re-engineer, so for example, in that case, if I've set up ranges in that 239 block, that I don't want to have to go back and change those group IPs around. I have to probably pay a vendor to come in and fix that application to do that. So I'd rather know upfront what that is. And of course, any reasonable sized enterprise has a change control process. The more I have to go in and make changes to the network, the more just time I spend in doing change tickets and sitting in change meetings and doing all that kind of fun stuff, peer reviews to get it done. The more I can one and done, the more time I have to do other things like clean my office, which I actually have been cleaning my office. Desk is not as piled with papers as it was. There we go. And multicast and wireless, good to know. I'm a believer in building that capability, and there are two different things you're doing about multicast for the wireless, and I've got a special appendix I'm building for wireless specifically, but it's good to know about, am I doing wireless multicast? There's a lot to consider. So thanks for watching. There's my YouTube channel. Like I said, I get enough subscribers just to be able to get a more reasonable, do a cut and paste, like grab this something if you can. It's on SlideShare. It's a PDF, so you should be able to get it from there, which SlideShare is part of LinkedIn nowadays, if you didn't know. You can follow me on Facebook. I only accept friends if I know you or otherwise associated. Twitter, not as useful, but it's there. Excuse me. And then LinkedIn is the one I'm really focusing on right now. And in the comments on the YouTube, wherever, if you want topics, or you have questions, or you want to get clarification on something, even if you want a little bit of help, I often do a quick, sort of 10-minute conversation, just to kind of get you pointed in the right direction. If it's, obviously if you need me, you need like 12 hours of work, that's a consulting agreement, we can talk about that. But just so, it's all there. I hope you're doing well. I hope, you are in confinement right now and safe. that hopefully this and other things are helping you manage the difficult feelings you're probably feeling right now based on this worldwide pandemic. That I'm wishing you all the best, and take care of yourself. Don't touch the face. Wash your hands. You know, as in the broadest sense, we're going to make it through. I know it's not going to be easy for a lot of us, and I wish you the best. Take care.